Hello everyone, this is Mr. Couple. Welcome to our second lesson during online learning. Today we'll be learning about specific heat capacity, and I am joined here today on voice chat by several students. They're going to be jumping in throughout the video. Just make sure, if you weren't able to make it, we miss you. Wish you could be here. All right, let's begin. So I want to start off. I just put this pot of water on the stove about 30 minutes ago, and I'm wondering, 30 minutes. I can't even talk. Ooh, okay. I just put this pot of water on the stove like 30 seconds ago. Like I just put it on the stove. And I want to know, in which situation is my finger more likely to get burned? So in this first situation, about 30 seconds ago, like I just started heating this thing up. I'm touching the metal on the bottom. And over here, I'm putting my finger in the water. So in which of these two situations am I more likely to get burned? If you guys want to jump in and just share your thoughts.
Uh, I think that in the first situation, just because metal conducts heat better than water does.
Right, so here I'm touching metal. In the second case,
Water.
I'm touching water. Okay, Fro, that's a good thought. Anyone else?
Yeah, I agree with what Pharaoh said because the particles in the water are gonna take longer before they start to heat up. So you'd feel the heat faster on the pot itself.
Yeah, I agree with you guys. So you could go test this out yourselves. Make sure that you do it early on because eventually that water is going to boil and you will really burn your fingers if you stick it in there. But since it was just a moment ago, like just 30 seconds ago, you will find that the metal on the iron, whatever this is, cast iron, is going to heat up way faster than the water does. So this is the main essential question for today. After a pot of water has been on the stove for a minute, why is the metal significantly hotter to the touch than the water? So why does this happen? Like what physically is happening that's causing the metal to be so much hotter than the water? Like they're both being exposed to the same heat source. What is it about these materials that's causing this weird thing to happen? So that's the first main idea for today. I'm going to reveal it. Different materials heat up and cool down at different rates. And so we're going to do a little experiment here. Obviously, like we can't do this for reals, so I'm just going to show it to you guys. So we're going to be doing an experiment where we're going to heat a sample of glass. So this is glass. And we're going to heat a sample of wood. And what I'll tell you about these two samples is they have equal mass and they're both supplied an equal amount of heat. So they're both heated at an equal rate. So the amount of heat that we're supplying, that's capital Q for heat. The amount of heat that we're supplying is the same. You'll notice that I've made sure that the bottom surface area of each object is identical, so they're both being exposed to the same amount of heat from the source, from the flames down below. All right, so down here, this is the results for our experiment, is we place both these objects above the flames, we wait for a while, and then we measure the temperature after a certain amount of time. They both started at room temperature, 20 degrees Celsius, and we're going to wait and see what the temperature is after they've been heated for some amount of time, like maybe you could say like 5 minutes or something like that. And what we find is that the glass reaches 49.8 degrees Celsius, but the wood only reaches 34.2 degrees Celsius. So first I'm going to have like a whole assortment of questions I'll be asking you guys about this situation. But first I just want to calculate the change in temperature of each material. So let's do that for the glass first. So how would we find the change in temperature? What would we need to do?
Final temperature minus initial temperature.
Final minus initial. So 49.8 minus 20. And so that gives us a temperature change of, let's see if I'm going to be able to do the math here. 4 minus
29.8.
29.8 degrees Celsius. And then if we find the temperature change for the wood, it's a similar process, 34.2 minus 20. And so we end up getting, that was a bad equal sign. What's that? 14.2? Did I do that right?
Uh-huh.
14.2. Math is hard. 14.2 degrees Celsius. So we can see here that the glass has had a much higher change in temperature than the wood did. And so this is going back to our main idea, is that different materials heat up and cool down at different rates. So even though both of these materials were the exact same mass and the exact same heat supplied to them, they did not change temperatures at the same rate. It took a lot, what am I trying to say? The glass heated up a lot quicker than the wood did. And so this is the first question I'm going to ask about this situation is the wood and the glass both have the same mass and the same amount of heat supplied. With reference to the thermal concepts from our previous lessons, so that's like temperature, heat, internal energy, explain why the temperature of each object did not change equally. So what do you guys think? So what was it about glass and wood that caused the temperatures to not change the same way? Any thoughts? It's a hard question, isn't it?
Um, I just think that some materials are like their structure is like either like more tightly compressed or expanded. I don't know.
So when you mean structure, you mean the
The
molecular structure.
molecules.
Yeah,
Yeah.
the molecular structure. Yeah, that's exactly right. So what's going on is that wood and glass have very different molecular structures. They're also made of completely different atoms that are going to be attracted to each other in completely different ways. So if we think back, I don't know if I ever told you guys about this, but we generally model molecules as being connected by springs. So here's an example of this is probably like a water molecule. I think that's your oxygen and then your two hydrogens off to the side. So we say like these atoms are attracted to each other when they're far apart and they repel each other when they're close. So this acts just like a spring. Like if I was to compress that spring down, it would push it away. And as it gets further out, it's going to pull it back in again. So we generally model the behavior of atoms like they're connected by springs. So here's a video of that. So we think like the molecules are sort of in this vibrational mode where they're attracting and repelling each other, like kind of like they're connected by a spring. The thing though is like it's way more complicated than that because the model actually has what we call degrees of freedom. And so it can like move side to side, up, down, back and forth. It can also like rotate in all different directions and then it can vibrate. So the particles are actually like very complicated motion that they're going through. And so realize that it's only one of these degrees of freedom that's actually captured by the temperature. So which of these, translation, rotation, or vibration, which of these is actually captured by temperature?
I would say vibration.
It's not the vibration. So temperature is the kinetic energy, right? So it's the average. I can't draw on this, I just realized. Temperature is the average kinetic energy. That's what relates to the temperature. So when we think about kinetic energy, only one of these is actually causing it to have kinetic energy, and that would be the
Rotation.
it's not the rotation, it's the translation, right? So we talked about how way back last semester we talked about how like there's two types of motion, like you can translate, like move across, or you can rotate. And when we defined kinetic energy, we only, without you guys knowing it, we were talking about translational kinetic energy. So when we talk about 1/2 mv squared being kinetic energy, that v is not rotational velocity, it's translational velocity.
Hmm.
So that's translational speed. And so what's going to happen is that the temperature can only tell us how quickly these things are moving through space. The temperature captures how quickly they're moving around this way. They're not capturing how much they're vibrating within each other. That's the potential energy. And it's also not capturing the rotational energy. So there's a lot more complicated motion going on here with these molecules than just the temperature. And so when we think about, well, yeah, so they have the same mass and they have the same heat supplied, but they don't have the same molecular structure. They're not going to move and vibrate and rotate the same way. And so that's going to end up, the temperature is going to end up changing differently. So, for example, with the wood, maybe more of the energy went into like the vibration of those molecules. And in the glass, more of it went into actually moving the molecules. So, depending upon how that energy that you're supplying gets distributed into the particles, you're going to get, or I should say molecules, you're going to get a different amount of translational motion, rotational motion, and vibration. And so that's sort of what's going on. And that's the answer to the question is like, why why doesn't the temperature change equally? Well, because there's three places where that energy can go. Let me try to draw a picture of this. So when we stick energy in, that energy can go to three places. So it can go
Hmm.
to translation, it can go to rotation, and it can go to vibration. And temperature is only catching the translation part. That's the temperature. So when you're looking at how the temperature changes, well, what if more of the energy went down into these places down there? What if you had like a bunch of energy going down there and only a little bit of energy going up there? Well, then that object wouldn't change its temperature as much. And so that would be the example of wood. That wood has more energy going down into the rotation and vibration and less energy going into translation, whereas glass would be the opposite. So every material basically has these built-in properties, and it's really really complicated. We're not going to get into like all the crazy mechanics. I mean, try to imagine what the equations would look like to model this motion. Like try to imagine what like how much mathematics you would need. You need like three-dimensional equations. You'd have to be like doing this it's really 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 complicated. So we're not going to go into that. I just want you guys to like loosely realize that when you add energy, when you supply heat to something, it doesn't just go to making the particles move. It goes into making them vibrate, and it goes into making them rotate. All right, what questions do you guys have for me about all this crazy stuff I'm talking about here? We good?
Yeah.
Okay, so we want a number that can tell us how much of the energy is actually going into translation versus how much is going to these other places. And that number ends up being something called the specific heat capacity. And you've probably heard of this before. It is in the ninth grade curriculum. So here's how we define specific heat capacity. First of all, we use the letter C for specific heat capacity. We say that the specific heat capacity of a substance is the energy required to change the temperature of a unit mass of that substance, by 1 Kelvin. So it's the energy that it takes to raise or lower the temperature by 1 Kelvin. So if we look at our temperature change here, we had a much higher temperature change for glass and a much lower temperature change for the wood. So my question is, which one has a higher specific heat capacity? And remember, it was equal mass and equal heat supplied. So the same amount of energy was given to the glass, the same amount of energy was given to the wood. Which one has a higher specific heat capacity? I'll give you guys a moment to either say out loud what you think it is or think to yourselves what the answer is.
Is it the wood?
Okay, so Sam is saying that the wood has a higher specific heat. Okay, so why would you say it's the wood?
Because with the same amount of heat supplied, the wood's temperature does not increase as much as the glass did.
So it would take more energy to change the temperature
One.
by 1 Kelvin. What do you guys think about that?
Yeah, I agree with Sam.
Yeah, that's right on the money. So what you could say is that the higher the specific heat is, the more energy it's going to take to change its temperature. And so what would that mean? Is like, well, what would we need to do to get the wood to get to the same temperature of the glass? What would we need to do to the wood to have it have the same temperature as the glass?
Increase the temperature.
We would need to increase the temperature further, and we would do that by adding more heat. And so that shows you that you would need to add more heat to the wood in order to reach the same temperature as the glass. So the wood has a higher specific heat capacity. You kind of think of it as like it absorbs more heat before it changes its temperature. So when you think about this picture up here, this is so gross. Uh, for the wood, when you add energy to the wood, more of that energy is going to be going into rotation and vibration for wood. Less of it's going to be available to go up into actually changing the temperature. Whereas with glass, more of the energy goes into translating it. And so it's easier to move the molecules of glass and harder to get the wood molecules to start to move. All right, so that's the basic idea. Yeah, you guys got it. Okay, now I'm pulling some Minecraft pictures over here. All right, so now I want to consider fire supplying heat to a block of wood. And I couldn't think of a better example than Minecraft for this. I want to identify all of the variables which could increase the temperature change experienced by the block. So what are all the things about this situation that we could change that would cause the wood to get an even greater amount of temperature while we're heating it? So just pop some ideas out into chat here.
The amount of time that it's placed under the
Yeah,
fire.
so we could leave it under the fire for more time. What that would end up doing is it would give us more heat. More time would give us more Q. And so if you have more Q, more heat, let me put heat. If we have more heat supplied to the block, then obviously it's going to get hotter. And what are some other things that we could change to get more temperature, a hotter wooden block?
Could you put it in the fire?
So that would also, yeah, so if you brought it closer, I could actually move this thing. So if I brought it closer into the fire, then yeah, there would be more heat that it would be trapping because it's closer to it. Heat sort of drops off like an inverse square law. It's called radiation, like thermal radiation. So yeah, if you brought it closer, it would get hotter. So more time or closer. But both of these are the same result, is you get more heat. What are some things that aren't heat related to increasing the heat that we could change about this scenario to get a greater temperature of the block?
Less mass of
Less
the
mass.
block.
Yeah, so if we have a smaller, so less mass. And there's one more thing we can change.
Mm,
This one's like, you got to think way outside the box for this one.
I don't know, adding more oxygen or something.
That would still probably result in more heat. You guys are going to get it. You just need to switch wood for glass.
I was gonna say glass.
If we put glass in there, like we showed up above, glass heats up faster than wood. So if we switch the block from being a wooden block to being a glass block, then it would heat up faster. So what I want to do is just create, I got my little pictures off to the side over here. So I want to create illustrations of all of this. So the first thing we're going to do is we're going to move it closer so that the flame is able to provide more heat to it. So that'll be our first one. And then the next one, I was supposed to copy it over. Copy, paste. Oh geez, what did it just? It put it at the bottom of the document. Doing this live. Okay, here. Okay, so I'm gonna bring the block closer to the flame so it gets more heat. The second case was I wanted there to be less mass. So I'm gonna do that by shrinking the block. So if we have a smaller block, it'll get hotter. And then the last one was switch the wood with glass. All right, so each of those would give us a greater amount of temperature change. And so let's talk about why the temperature change is increasing. So here, the temperature change has increased because we've added more heat. So there's a direct relationship between temperature change and heat. In the next situation, we've increased the temperature because we've decreased the mass. So what relationship does temperature change have to mass?
The less the mass, the more the temperature.
The less
So it's
mass, the more
inverse.
temperature. So it's inverse. So I have to write that as 1 over m. And then the last one is we've replaced the material with something that had a lower specific heat, and that gave us a higher temperature change. I should have done this for all of these. Less mass gave us a greater temperature change, and then more heat gave us a greater temperature change. And so for this last one, the glass has a lower capacity, a lower specific heat capacity, and so it is able to have a greater temperature change. And so that's also an inverse relationship. So we have these three um, proportionalities. And so from this, we want to build an equation. So you'll notice that on the left-hand side for all of these, we have delta T. And so we'll leave delta T on the left-hand side. But on the right-hand side, we're going to have direct to Q. And then, that was a gross Q, direct to Q and an inverse to mass and specific heat capacity. And so that's, now we're including all of the variables that can affect the temperature. So the three variables that can affect temperature are how much heat do you add, how much mass do you have, and what material is it. Now that all of the variables are present, we switch this to be an equal sign. We generally like to solve this for Q. So solving for Q, we would have an equation that says Q equals MC delta T. And that's the specific heat or I guess it's usually called like the heat equation. So that shows you how the amount of heat that you supply to material, how does it affect the temperature change that the material experiences? And you can see that it's based on two properties of the material. It's based on the mass of the material and it's based on the type of material. So roughly speaking, you can see how clearly if you increase the heat, you're going to increase the temperature change. But what determines that is the material properties, how massive it is, and what type of how the molecules are structured and things like that. We good?
Mm-hmm.
Just checking in. See how much time I have left. I have about 10 minutes. Okay, what we want to do now is we want to use the data from that experiment. We want to determine the specific heat capacity of both these substances. So starting from Q equals mc delta T, to find the specific heat, we need to solve this for C. So C is going to be equal to Q over M delta T. All right, now I'm going to give you guys the available data up here. So I'm going to say that they're each a mass of 10 grams, and the heat supplied was 250 joules. So if we do this calculation, we'll do it for the glass first. So the heat was 250 joules. The mass was 0.0. I'm going to mess this up. Is that 10 grams? Yeah. Whoop, it's not grams anymore, it's kilograms. So 0.010 kilograms. And the temperature change for the glass was 29.8 degrees Celsius. Okay, so now we just got to grab a calculator. Let me see if I can find my calculator. I think I had one on my desktop. Let me find it. There it is. You're going to pop up calculator. It's not. Oh, what the? Why is it over there? Well, there's a bunch of them. I clicked it too many times. I can't even see the whole thing. I give up. I'm just gonna do it. I'm just gonna do it on my phone. You guys could try it too if you have a calculator. I'm getting someone's mic. Hearing myself.
Yeah, we got echo.
Okay, I got. Tell me what you guys got.
Mm,
I got 74.5.
Did you?
Oh wait, no, I multiplied.
I got
got
840.
Yeah.
There you go. Who's? I'm gonna have to mute whoever is doing this. It's Laura. Okay, sorry, Laura. I had to mute you. Okay, so now what's the unit? So if we look at the units over here, we're gonna have joules per kilogram per degree Celsius. So that's the unit. Generally, this is written as joules per kilogram per Kelvin. Now here's where I don't remember. I just noticed my webcam's not up. I don't remember if you guys remember we talked about Celsius and Kelvin, but if you have a temperature change of 1 Celsius, it's the same as a temperature change of 1 Kelvin. And so that's because the Kelvin is set based on Celsius. So they're always 273 degrees off from each other. So if you gain a Celsius, you've also gained a Kelvin. So we can interchangeably use for temperature change only. This only works for changes in temperature, not for absolute temperatures. But if you have a change in a temperature, you can always just replace Celsius and Kelvin with each other. All right, so that's the specific heat of glass. So this is for glass. And so to find for wood, we do the same thing, but we would change which number?
it would change the temperature change.
The temperature change would change. So 0.01, I forgot to put the unit. And then my temperature change would be 14.2. So what's going to happen if we're dividing by a smaller number in that temperature slot? What's going to happen to our answer?
It's gonna
Get a bigger
We're going to
number.
get a bigger number, which is exactly what you guys said above, was that the wood has a higher specific heat capacity because it had a lower change in temperature. So you'll be dividing by that lower temperature change, giving you a higher specific heat capacity. So it's 250 divided by 0.01 times 14.2. So I got 1,760, so I'll just round it off to 1,800. All right, so that's the main idea, guys. I have some worked examples I was going to do if there was extra time, but this is basically specific heat capacity. So what you need to remember is that it's a material property. So I'm going to go back over the main ideas. So different materials heat up and cool down at different rates. So it's important to realize like this isn't just for when they get hotter. This is also for when they get cooler. So this is not just the amount of energy you need to add to gain a Kelvin. This is also the amount of energy you need to remove to lose a Kelvin. The second main idea was the amount of heat supplied to a unit mass of a material to produce a unit change in its temperature is called the specific heat capacity of the material. We almost never call it specific heat capacity. Most people just get lazy and just call it specific heat, but it is supposed to be called specific heat capacity. The specific in physics, you'll see this a lot. Anytime you hear something called specific, like for example, just yesterday with the second year SL kids, I was teaching about something called specific energy. And specific energy is the amount of energy that can be extracted from a fuel per unit mass that you burn. So specific is always related to unit mass. So it's always like a per kilogram. So anytime you hear the word specific, it's a per kilogram type of thing. And then the last thing was the specific heat of water is nearly 10 times greater than iron. And so that's answering this question here. So iron has a much, much, much lower specific heat capacity than water does. So when we're heating both of these things, the iron is going to heat up way quicker because it takes less energy to heat it up. And so that's why my finger got burned from the hot metal, but it doesn't get burned from the water because the water is going to change its temperature uh, less because it has a higher specific heat capacity. The specific capacity of water is unusually high. It's over 4,000 joules per kilogram per Kelvin. Like that's a ridiculously large amount of energy. Water is a really good absorber of heat. The reason why is because when you add energy to water, a ton of it goes into the rotation and the vibration of the thing. You can see how lopsided the water molecule is. Like it likes to sort of tumble around and spin. There's also really strong bonds here between the oxygen and the hydrogen. So they have like a really strong connection. The interparticle forces are very strong. So most of the energy goes into that into potential energy. All right. So those are the three main ideas. Is there anything else I can ask you guys want to ask me before I solve some example problems?
Mm,
Nope.
All right. So much time I've got on this video. My clock says about 2 minutes. So we'll go ahead and start working on these. I'm probably not going to finish them on the video, but that's okay. I'll just post the solutions to them. A quantity of heat equal to 9,800 joules is absorbed by a piece of iron, and the mass of the iron is 1.8 kilograms. Calculate the temperature increase of the iron. The specific heat capacity of iron is 450 joules per kilogram per Kelvin. Okay, so we want to find the temperature increase. So the way you find the temperature increase is you find the change in temperature, and it's going to be Q over MC. That's from the equation Q equals MC delta T. So we know how much heat was added. It was 9,800 joules. We just need to divide by the mass, which was 1.8 kilograms. What the heck? 1.8 kilograms times the specific heat, which is 450 joules per kilogram per Kelvin. So if we look at the units here, you can see that the joules are going to cancel out. The per kilogram and the kilogram is going to cancel out. We're just going to end up with a 1 over per Kelvin, which is just a Kelvin. So if we throw all these numbers in, let's see, 9,800. I got to figure out how to get my calculator to display correctly. 450. So I get 12. And you'll notice that I'm putting degrees Celsius. Whoa, excuse me. I got a cough for a second. All right, sorry about that. Oh, my timer's off. You'll notice that I put degrees Celsius. So why did I do that? Because clearly the unit was supposed to be Kelvin. So why did I put degrees Celsius?
Because it was a change in temperature.
Yeah. Any other reason? You're right, but why not? Why not Kelvin? Like, shouldn't this have been Kelvin? Why did I put Celsius and not Kelvin?
Uh,
The answer is there's no reason. That's just how I did it. Usually, like when scientists are in a lab, like doing problems like this, you're like heating up iron or water, like you're probably going to use Celsius. But if you're doing like really like low temperature physics where you're doing like in some crazy domain or like really high temperatures, then is when you switch over to Kelvin, because Kelvin is more appropriate when you go down to like, you don't want to have negative temperatures. And so Celsius sucks because if you go below freezing, it's going to be negative, and you wouldn't usually like using Celsius in those domains. But you could use Celsius or Kelvin interchangeably. Just remember that you just add 273 to the Kelvin and it becomes Celsius, or you subtract 273 from the, I'm doing this backwards, aren't I? You subtract 273 from the Kelvin. My brain's not working right now. I'm trying to remember. Do you guys remember what it was? Yeah. You add 273 to Kelvin, it becomes Celsius, or you subtract 273 from the Celsius and it becomes Kelvin. Did I do that right? Yeah. Anyway, but the fact of the matter here is that this is a change in temperature, so it doesn't matter which unit you use, because a 1 degree change plus 1 Celsius is the same as plus 1 Kelvin. But 1 Celsius is not equal to 1 Kelvin. So 1 Kelvin would be way down here, like near absolute zero. So absolute zero would be actually the coldest possible temperature, whereas 1 Celsius would be like up here at 274 Kelvin. But a gain of 1 Celsius, so if I gained plus 1 here to 2 degrees Celsius, that would be 275 Kelvin. So gaining 1 Celsius is the same as gaining a Kelvin. That's all. All right, I'm going to stop the video now. If you guys want to stick around and voice chat, we can. But I'll see you guys later.